Good afternoon. Welcome to the CMU SubT Spring Update. My name is Chris Kissel, Associate Director of Corporate Partnerships in the School of Computer Science here at Carnegie Mellon University. Thank you for joining today's event. Just a few housekeeping items before we begin. Please note, this event is on the record and is being recorded. If you'd like to pose a question, there is a button at the bottom of your Zoom screen that says Q&A. Please post your question there at any point, and we'll put it in the queue for consideration during the open Q&A session after the main discussion. We are pleased to kick this event off with a brief recorded welcome by Congressman Mike Doyle. Congressman Doyle has been a champion for robotics since he was elected to Congress, not just for the universities and companies in the Pittsburgh region, but for the nation. He recognizes the power of robotics to inspire. His passionate leadership over the past 2 decades has been integral to the transformation of Pittsburgh. Congressman Doyle sits on the Energy and Commerce Committee, where he aggressively supports broadband access, energy-efficient technologies, and R&D strategies to ensure the U.S. remains globally competitive in the 21st century economy. Congressman Doyle.
Good afternoon. I'm sorry I can't be with you in person, but I'm pleased to be able to welcome everybody to CMU's Team Explorer Update. I'm excited to have this opportunity to highlight a robotics team that is successfully competing with its teammates from Oregon State University and yet another DARPA Robotics Challenge, this time the Subterranean Challenge. I co-founded the Robotics Caucus in 2007, which has given me the opportunity to see firsthand how far robotics has come since then. But Carnegie Mellon University in my hometown of Pittsburgh has been a leader in robotics since it's launched the first robotics PhD program in 1976. The Robotics Caucus has worked to do its part to propel robotics into the national imagination. We established National Robotics Weeks, for example, an idea that quickly took off with the help of both the robotics industry and academia. Now, every April, across the country, events from student competitions to startup showcases take place in schools, on shop floors, and even in festivals in closed-off streets that showcase the creativity and imagination of American roboticists. It's been decades since Americans first recognized the urgent need for a subterranean robot. That was when Carnegie Mellon rushed to develop a robot to help clean up the damaged nuclear power plant at 3 Mile Island outside of Harrisburg. Since then, we've seen tremendous impact that robotics can have on people's lives. From small robotic toys developed specifically to help engage children with autism, to autonomous systems, also developed in my hometown of Pittsburgh, that can traverse deserts and distant planets, as well as navigate city streets and extend the touch of a surgeon. There has always been great aspirations for robotics, and while many aspirations and dreams are becoming reality today, there is still much more work to be done. The Subterranean Challenge is yet another example of new technology being developed that will have an impact far beyond our imagination. The accomplishments of the teams competing in DARPA's Subterranean Challenge mark another milestone in improvements in robotic systems that can be deployed to keep humans out of the dark and dangerous environments like caves and tunnels. Robots like these someday, in the not too distant future, help our first responders search for and rescue lives during disasters like earthquakes or mine collapses, or keep our military personnel out of harm's way by conducting autonomous scouting missions. I understand that the team is already working with SOCOM to test and evaluate the system they've developed for future missions. The pace of innovation today is incredible, and the work of the Carnegie Mellon team and their Oregon State University teammates shows that ingenuity and innovation in the U.S. is alive and well. It's our role in government as leaders to help support this type of work now and for years to come. I'd like to thank CMU and Team Explorer Sebastian Shearer and Matt Travers for inviting me to kick off today's update this morning, and I wish them all the best as they head into the final leg of competition this fall. And even more importantly, I look forward to seeing the technology that they've developed over the past few years deployed in robots to improve people's lives. I hope everybody enjoys the team update. Thank you.
Thank you, Congressman Doyle. Today, I am joined by SubT Team Explorer Leadership, Sebastian Shearer, Associate Research Professor, and Matt Travers, System Scientist, both faculty in the Robotics Institute in the School of Computer Science at Carnegie Mellon University, and Geoff Hollinger, Associate Professor of Mechanical Engineering and Robotics at Oregon State University. At this time, I'd like to turn things over to Matt Travers and Team Explorer.
Hey, thank you very much, Chris. Thank you very much, everybody, for joining. So we're going to run through a short set of slides just to set some context here. So if we want to go to slide 2, I think we're good. All right, so before we actually introduce the team and introduce the demo and specific technologies, we wanted to give a bit of high-level overview onto the DARPA challenges and sort of provide context for where SubT sort of fits in our overall ecosystem. So on this slide, what you're looking at is sort of a history of all of the DARPA challenges. And this is, excuse me, you're seeing some of the DARPA challenges in here, but you're basically looking at the timeline associated with those challenges and autonomous driving. So the message that we're trying to convey here is really the impact that DARPA challenges can have, right? So we're taking basic technology, things that are being developed in the lab, being developed, Carnegie Mellon, other universities across the nation, and then the DARPA challenges really typically act as a catalyst for getting technology out of the labs and really getting it, to the point where entire industries can be created, right? So the overall impact of DARPA challenges was the thing we really wanted to start out with. And just that the idea, right, that we're taking technology, we're increasing the technical readiness level, and we're actually, we're competing in the challenges today. And the idea is that we're moving towards commercialization and greater utilization of the technology. So if we can go to slide 2. Sorry, slide 3. All right, so this gives you a bit, sorry, to the previous slide. To show the DARPA challenges. There you go. All right, cool. So here you're actually seeing a timeline of Carnegie, well, some of the work, in fact, that Congressman Doyle was just explaining, where the robots, originally for Carnegie Mellon, we started putting robots underground. Relative to that previous timeline, where we are in the technological development when it comes to underground robots. So the previous, starting in the 80s, technology is being developed. We're now currently in a DARPA challenge. And the real question is, where do we go from here, right? Where are the companies, what is going to be industrialized, and really where's the impact, the true impact going to be? All right, if we can go to the next slide, please. All right, so introducing the actual Subterranean challenge. So this started back 3 years ago, and it was 3 circuit events. They were going to focus on 3 different environments. So there was tunnels, was the original competition circuit event. Then there was an urban event, which happened 2 years ago, or excuse me, last year. And then there was supposed to be a 3rd circuit event, which was going to be in caves. That 3rd circuit event was actually canceled due to the COVID, what we're dealing with right now. But as we're moving towards September of this year, the final competition is taking all 3 of these environments and putting them together. And the overall goal is to go out and locate artifacts. So the robots are, acting in a very autonomous way, and they're searching these different terrains, these different types of environments, and they're trying to locate artifacts. So they have to build a map. There's no a priori knowledge. So they're going out blind, and they're searching these environments. So that's sort of the overall goal. And I think in the next slide, we're going to start to introduce what the artifacts look like. But the overall goal is to be able to go and search these environments as fast as you can and to locate artifacts with as much accuracy as you can. Cool. Thank you, Geoff. I'm going to turn things over to you.
Great. Thanks, Matt. So I'm Geoff Hollinger from Oregon State. I lead the Oregon State part of the team. I wanted to talk just a bit about some of the other teams that are competing in this challenge to give you a sense of how competitive the field is. So you can see that many of the major players in robotics, in addition to CMU and Oregon State, of course, have teams here. So JPL, MIT, ETH, University of Nevada, Reno, Berkeley, Georgia Tech also had a team. UPenn had a team in the first circuit. So here's a list of the various different teams, and they're all taking various different approaches. Moving on to the next slide, talking about our team, we have two universities, as you heard from the intro with Congressman Doyle. Carnegie Mellon University is the team lead, and Oregon State University is supporting the team as well. For CMU is focusing on the hardware, and then portions of the software support, including perception, simultaneous localization and mapping, planning, coordination, the executive level, the base station, and object detection. Currently, Oregon State University is focusing on coordination and object detection, though in the early circuits, we were also participating in the base station design as well. Now, Oregon State University also helps with testing, and this has been more difficult with COVID because of the remote situation, but previously we had visited CMU a number of times and participated in the testing and helped to ensure that the system was robust and fieldable. This is a picture from the tunnel circuit, which we were victorious over the competing teams. And you can see the robots in the foreground there, which we're going to talk more about later. Moving on to the next slide. The objective of the challenge is to find, classify, and localize as many artifacts. And so the artifacts are things like backpacks and dummies that look like humans, survivors, vents that may have hazardous gas coming out of them, objects of interest like drills and fire extinguishers, various different things, and different things that vary depending on the circuit. So the cave circuit has certain artifacts, the urban circuit has certain artifacts, and the tunnel circuit also has certain artifacts. So what we want to be able to do in this challenge is map the environment, locate these artifacts, do object recognition on them, and register them to the map and send the location back to DARPA. In order to successfully score a point, we need to be within 5 meters of the DARPA defined coordinate frame. So that's how accurately we need to localize the artifacts. We only have 40 attempts, so we can't just spam various different locations and hope to get lucky. And there are about 20 artifacts present in the course. So the maximum score would be 20, and whichever team gets the highest score, finds the most artifacts and localizes them, wins whatever leg of the challenge. Moving on to the next slide. So these are some of the research challenges and the systems level challenges that are in place that are tested by the Subterranean challenge. So this is a GPS denied environment. And there are in many instances sparse features. So this is very difficult to localize and build a map for that. You have significantly degraded sensing. There's low light. Various things are obscured from the robot's view, and also scattering conditions for the various different sensors. And so this is a major challenge in terms of sensor fusion and utilizing things like cameras and lasers in this kind of very difficult environment. There's very severe communication requirements, physical impediments, and link reliability is very difficult. We have dynamic terrain where the environment changes as DARPA has put various different obstacles in the environment that can change over time. There are also endurance limits. So operationally relevant to the spatial scales, we need to move quickly and we need to be able to traverse the environment quickly and map it and localize these obstacles in a very rapid fashion. Finally, there are significant obstacles in the environment and terrain features. So the mobility in the environment is very challenging as well. So this requires us to deal with perception, autonomy, networking, and mobility together in order to solve the challenge. Moving on to the next slide, and I will hand off to Sebastian Shearer, the CMU team lead, to continue.
Thanks, Geoff. So one thing I just wanted to say, I think we didn't say this before, we have a big surprise for you in that we are going to do a live demo of our robots, and that's why we are all wearing masks, and we are in a location that doesn't have very good internet, but hopefully good enough for this talk. So I just wanted to kind of, there's a big surprise and some excitement coming up. I'll give you a little bit of a high-level idea of where we are trying to get to. And so the two high-level themes of our approach is one, this idea of modular autonomy. Can we take both on the software and hardware level these things to be able to rapidly reconfigure the robots and rapidly change them as conditions require? And the second idea is this idea of having resilient autonomy. And the idea there is, can we make the system robust, for example, through having redundancy or having some multiple solution paths, Can we have solution diversity? Can we somehow bring creativity into the system to, in the end up with a resilient system? If you can go to the next slide, please. And so to build this modular autonomy system, there are many components that we have to build. So the perception system, there's a lot of work in terms of the SLAM, sharing maps, object detection, map fusion, and then taking this information, making decisions for exploration, planning, and how we deploy comms nodes. And then this information is used by robots to make decisions about where to go, and the operator also can give us some inputs. And so I think we can go to the next slide. So this is the team of robots that we mainly focus on right now is the 3 ground robots plus 4 drones. And the drones are on the back of 2 of the ground robots. And there's also a more optimized kind of sensor payload that will go onto a walking robot. Okay, if you can go to the next slide. So in the 2 prior tunnel events, we played first in a tunnel circuit and then second in the urban circuit, and getting ready for the final competition. So if you can go to the next slide. So to give you a bit of an agenda, so our goal is to, we'll now hand it over to 2 students in the team that will talk more in depth about 2 particular aspects. You saw this big wheel of capabilities, but we just wanted to highlight kind of two technologies that are interesting, and we'll give you a little more in-depth presentation on this. And then we'll attempt something novel to us in the sense that we have never tried this before, is to do a live demonstration of flying our drone on the qualification course. And after that, we'll do an Ask Us Anything. So basically, please post some questions in the Q&A as you think about them, and then we'll do a big question and answer later on. Okay, so okay, yeah. So I'm like to introduce Rohit Garc. He's a master's student in the lab, and he's been working on the aerial exploration.
Hello, everyone. Basi already introduced me. I'm going to be giving you a brief overview of the aerial exploration pipeline that is on our drones. Okay. Our exploration strategy is based on a popular approach that uses frontiers to guide the robot towards informative regions within the environment. This figure on the left is a graphical representation of what the classical approach looks like. In this, frontiers represent the boundary between known free space and unknown space. The key idea being that in order to gain the most new information about the world, the robot must move to the boundary between open space and unknown space, thereby continually pushing back the frontier boundaries as more of the environment is discovered. Our approach introduces several modifications that improve the overall performance of the classical approach. We leverage a larger map built by the LiDAR to estimate the volume that has not yet been observed by the object detection cameras. This volume can be calculated by subtracting a sensor observed map that tracks volume observed by the cameras from the global LiDAR map that tracks volume observed by the longer range LiDAR sensor. We then place frontiers in this subtracted map, cluster them, and then sample viewpoints pointed towards these clusters. These viewpoints are what the drone eventually plans to. The figure on the right illustrates the approach. This is a top-down view of a limestone mine that we go to for field testing. You can see the sensor observed map shown in green, the global LiDAR map shown in gray. Frontier clusters are shown in solid white circles, and viewpoints sampled around them are shown as yellow arrows. We have seen that this approach allows for a better distribution of clusters and viewpoints in unexplored regions while keeping noisy frontiers to a minimum. So you can sort of see that when you look at this map, you see that all these viewpoints are very well spread out, and you find enough viewpoints in all the different tunnels. So this is something that we think has been a big improvement for the classical approach. Next slide. The figure shown here illustrates the viewpoint sampling step that follows the frontier generation and clustering. It generates camera poses which, when tracked by the drone, enable camera coverage of the environment. It's an important step that gives us the ability to discover hidden artifacts such as fire extinguishers, drills, helmets, amongst other objects that we're supposed to find and report to DARPA. We uniformly sample multiple points at varying distances from the frontier cluster centroid, as well as varying heights. These points are collision checked and then passed on to the planner, which uses a weighted algebraic equation to select which viewpoint to plan to, and then generates a trajectory to the selected viewpoint. The viewpoint selection equation factors in things like Euclidean distance between the robot and the viewpoint, the change in robot momentum, and frontier scores generated from shared coordination maps. Next slide. Now I'll be giving you a sort of like an overall overview of our entire autonomy architecture. The boxes in blue are the packages that form each module, and the ones in orange are the relevant maps being built or worked on within the module. Starting from the top left, we have the map building part that uses dense point clouds generated from the SLAM pipeline to build an occupancy grid map. To its right, we have a map interface API that allows us to work with the grid map and do things like collision checking. To this grid map, we pass this to the map processing part of the pipeline using the interface API. This is the part that generates frontiers, clusters them, and then samples viewpoints to those clusters. Those viewpoints are then fed into an RT Connect-based global planner that plans trajectories from the current robot pose to a selected viewpoint. A progress monitor tracks progress of the drone along the computed global plan and feeds waypoints to the local planner, which plans local collision-free trajectories to the waypoint. We actually have an ensemble of planners, each serving a specific purpose. The primary planner being the RT Connect-based global planner. We also developed a stuck recovery random walk planner, which allows us to move the drone away from regions it may get trapped in, such as dusty areas where the local planner might not find. So if the drone is not making enough progress along the generated global plan, it switches to this random walk planner to get it unstuck. In addition to that, we have a graph management system that builds a graph consisting of key poses visited by the drone, connected by collision-free paths between the key poses. A third planner called the graph planner is employed that uses this key pose graph to navigate home once the drone decides it's time to do so. We also have the ability to share maps containing information about volumes explored by each robot between all robots in the system. That's shown by the inter-robot map sharing module at the bottom left. These shared coordination maps are coarsified so that they can be efficiently transmitted over the network. This biases the robots away from each other and minimizes overlap in explored volumes between them. That concludes this overview of the aerial autonomy exploration pipeline. I will now be handing this over to Shibo, who's going to be talking about the SLAM pipeline.
Hello, everyone. My name is Shibo. I'm the first year PhD student from Robotics Institute. Today, I would like to introduce SubT, ambient-centric leader visual inertial estimator for challenging environments. Could you please go next slide? Yeah, so robustness is a great challenge for the SLAM today. So SLAM still not works well in the challenging environment such as low light, motion blur, and the geometry degraded environment such as dust and long corridor. So to solve this problem, we believe that an ideal SLAM solution should be fail-safe and failure-aware. For example, the systems should be aware of the incorrect data association and hardware failure. Could you please go next? However, we found that most of the SLAM system cannot overcome this challenging environment because of the sensor itself is environment dependent compared with these sensors. And we found that MU is not environment dependent. So there is little to no outliers. Could you please go next? So here is a comparison between the Vero camera. You can see that the only drawback from the MU is that it cannot achieve the accurate estimation from the long term. So because of this, our system follow a key insight is that we believe that MU can be extremely accurate as long as its bias drift can be accurate estimated. So our SLAM system is an MU-based SLAM system. Could you please go next? So here is the architecture of the SLAM system. You can see that we put the MU odometry in the center because we are the MU-centric. Basically, we didn't try to solve the big factor graph problem. We tried to divide the big factor graph into several sub-factor graphs. We have the visual odometry factor graph, laser odometry factor graph, and MU odometry factor graph, and actual. And each factor graph try to provide the relative pose prior to the MU odometry and try to estimate the bias of the MU. And the MU odometry itself will provide the prediction to each factor graph. So in the normal terminal environment, you can see that because there is no big temperature difference, so the thermal camera will be degraded. So we will directly achieve the laser visual inertial estimator. Could you please go to the next slide? So in the very degraded environment, because the visual camera will be degraded, so we will directly achieve the laser thermal inertial estimator. Move to the next slide. In the geometry degraded environment, so such as a long corridor, so we will directly use the visual and thermal together and to achieve the visual thermal inertial estimator. Could you please go to the next slide? Here is experiment results. Could you please play the video? Here is the results, the performance of super odometry in the geometry degraded environments. So you can see that it's a long corridor. So we compare the super odometry and with another famous work, Leo-san. And you can see that Leo-san began degraded in such an environment because it lacked constraint in the forward direction. However, super odometry, because they also use a visual odometry constraint to estimate the forward direction, so it can still work well in such environment. So you can see that there is a significant drift in the Leo-san algorithm. However, compared with the Leo-san, super odometry can still work well, and the map result looks very good. Could you please go to next slide? We also test super odometry in the visually degraded environments. In this environment, and we just handheld the sensor and with a very aggressive motion. And you can see that the image from the visual camera is almost dark. So we cannot get reliable visual features for the super odometry. But the super odometry can automatically reject the unreliable visual features and make use the laser constraint to achieve the robust state estimation. So could you please go to next slide? Yeah, we also test the superodometry on both violate and the geometry degraded environments. And we run superodometry with autonomous flight in the cave environment. You can see that there are a lot of dust in the environment. So because of this, loam and Leo SAM began to degrade in such environment. However, because superodometry can select the most informative measurements and achieve robust estimation, so superodometry can still cope with this scenario. The estimated trajectory in this data set is around 500 meters. So it's a very long trajectory, but we don't find a significant drift in the slam. So the endpoint error is within 5 centimeters. Okay, could you please go to next slide? Currently, superodometry has been fully tested on UGV, UAV, and a lag robot. And also it supports OS1, OS0, and Valentine. Could you please go to next slide? Yeah, okay. Let me summarize the main advantages of superodometry. So we think that the first, I think that our amniocentric sensor fusion architecture can enable to achieve the robustness and extendability because it combines advantages of loosely coupled method with tightly coupled method. The second thing I want to share with you is that I think superodometry is simple but effective because superodometry avoids complex math to fuse multiple sensors. As long as sensors can provide a relative pose per wire to constrain the bias of MU, this sensor will be added in the superodometry successfully. The third thing I want to share with you is that I think Super has a low CPU usage and can achieve high real-time performance because the superodometry didn't try to solve the big factor graph optimization problem. And it divides the big factor graph into several sub-factor graphs and tried to use MU pre-integration to solve the problem from the cross-confined manner, which significantly increased the real-time performance. Here is one lesson I want to share with you is that we believe that MU could be a very extremely accurate as long as the bias drift could be constrained by other sensors. Yeah, could you please go to the next slide? Yeah, thank you very much for your listening. This is all for the superodometry. Thank you.
Thanks, Hugh. Okay, now we come to the experimental part of the program. So we'll get started with the demo. So I'll turn my camera around here so team can wave. So here's our ground robot and the drone. So, and then we have the base station over here. And so we'll start with calibrating the ground robot to our Darpa gate. Based this dark spot back there is where our start gate is, and I'll walk back there in a little bit. And then, so we have the drone on the back of the ground robot. See the IMU, and then the camera in the front, and the cameras. So we'll move the ground robot forward to the start gate now. .502. Yes. 0.502. Negative 0.046. Yes. Negative 0.046. 0.957. Yes. 0.957. Yeah, we're currently calibrating the ground robot. Calibrating. Error is 4 centimeters. Yeah, calibration is looking good. Generating T-pose. Okay, so regular competent robot would be exploring at this point, and then at some point the operator would decide, hey, here's a good spot where I want to launch the drone, and now we'll start launching the drone. Okay, and now we're launching the drone. So the drone is now being turned on. So it's actually turned off when it's on the back of the robot. So the computer is going to boot, and then the robot will unlatch from the ground robot and then take off. And John is going to follow the robot. So a safety pilot in full dust mask. It's pretty dusty in here. So the robot's expected to take off, then it will hover for a little while to estimate biases, and then should fly through the tunnel and start exploring, and then we'll start planning to show you our base station interface, and you can see kind of what the operator would see as the drone is exploring. So it's just initialized the drone. And when it's ready to take off, it will turn on the lights and then start taking off.
Well, since Zoom seems to have a high pass filter on the loud noise, I can narrate a little bit here. So here you can see the drone trying to explore the environment. So it notices that very small opening that it will then be flying through. So it decides that it wants to attempt to fly through that narrow opening that it can make it through. And there it goes. And so one of the challenges in the competition is having those narrow passages and having artifacts that are behind them. And so the need to get through those narrow passages with both ground vehicles and drones is very challenging in terms of the mobility requirements. And here you can see the view of the robot. So this is the map, what it's seeing from the camera, and also the SLAM map that it's building. So you can see UGV1, that's the ground vehicle. And then the arrow is pointing to where the air vehicle is exploring the environment. And also see the operators at the base station there on the video.
Okay, yeah, I had muted the sound a bit because it was noisy.
So
yeah, so the drone's exploring right now. We have this narrow passage in the beginning to give it a bit of a challenge. And of course, there's a demo effect. This is the first time it has hung out in front of the tunnel so long. But that's why it's fun, right? Do this in real time. So yeah, so this is, you can kind of see what the operator is seeing on the base station. So we do send a kind of low-res camera stream just to give a little more awareness to the operator. And then kind of main interface is really the 3D map for the operator to have an idea. So it was going down a hallway here. Now it's decided to enter what we call the gas room. So ideally, it should be able to detect some gas in here. And then here it also is just flying in front of a backpack. And then you can see that the carbon dioxide measurement is already going up here around the yellow arrow. So there are a couple of artifacts in this room. There's a cell phone, I think, also in this room, right? Right here. Yeah, there's a cell phone and a backpack. And then actually the gas is in that, where the Ryan is moving cursor right now. Actually, it's just entering the room where the gas artifact is. It's to the right. It's a gas bottle, a CO2 bottle. Yes, and you can see the highest value right now is in the gas room, and it actually put it in the middle of the room, the artifact. We actually report at the door, but it puts it where it thinks the highest value is. So now it is done exploring. And so it should continue further down the hallway to see if there are other artifacts down there. So here's another room. That room is a little harder to enter. It has a barrier that blocks roughly half the door. And so I just flew over the barrier, and so it's looking in that room. There are a couple of artifacts in that room as well. There's a rope and a drill, and I guess another cell phone. There's another cell phone in there as well. Yep, right here. And a helmet. There are actually two, and here you can kind of see the drill in the picture. And there's detected a drill as well. So it's actually exiting through the door. And it looks like it's deciding to explore some of the other rooms it has skipped.
So there was a question about what the ground vehicle was doing while the drone was exploring. Basti, maybe you want to comment on that.
Yes, so here we are essentially testing only the drone. In a real situation, the drone would be launched inside the course, maybe a couple hundred meters or however far inside the course. And once the drone takes off, the ground robot starts exploring on its own. So here we're basically not testing the ground robot, but nominally the ground robots would be exploring. And here we just flew past the survivor. And let's see. some point the drone's gonna come back home. I don't know if that's already. Yeah, I think it's gonna explore that section it skipped when it flew out. And here's another backpack. And here's a graffiti. That's not part of the competition. I guess it has more battery left, so it's deciding to explore another room. Yeah, looks like maybe now it decided, okay, I'm out of battery, and it's coming back home. And so it decided there was some problem in terms of the flight time estimate. Is it trying to do an emergency landing or not yet? It's still landing at home. Ryan, what is it doing?
Yeah, landing at home.
Okay, it's trying to land at home. Okay.
I had a quick rewind.
Oh, okay. It quickly thought it could make it through the door. Yeah. So yeah, so the operator knows what the robot is thinking by looking at what's called a behavior tree. It's essentially a slightly different way of doing a state machine, and we send that for every robot. So the tree is pretty big, but you know which states the robot goes through. And so what happened now is that it had trouble getting through the door, so it ran out of time to go home, and it keeps track of the best place to land in case of an emergency, and decided to land there instead. Can you? So I guess now so you can kind of see what the map looks like that it built. So the colored map is what ground robot built. The red map is what the drone built, and then you can see the artifacts that are highlighted. And then this kind of streak of colored points are the gas measurements that are above the threshold. And then so next we'll show you kind of what there's some artifacts that it detected. So here's an example. Survivor that it detected, and we can also show that to you in the 3D map, maybe. Mm-hmm. So yeah, so it's up in the corner where Ryan's moving the mouse, and then when we're happy with it, we can submit that artifact, and we got a point. So that's how it should work in the competition if everything goes. Thanks everybody, and I think now next we're going to the ask me or ask us anything phase. So I think let's see. In terms of, so there was a video, but I think maybe it's better to ask some questions. Okay, how much computer vision research goes into creating these robots? A lot. So I think, and then we are not using a T265. It has an L515 depth camera that we're using for seeing up and down on the drone. The cell phones are detected in using the Wi-Fi, just scanning for Wi-Fi. We have some visual detection, but it doesn't work too well because they're so small and the appearance changes a lot.
Yeah, it's been Sorry. Yeah, so it's being, or on the cell phone is being taken. The processing is definitely being done on the drone. So yeah, there's a constant, like trying to optimize the size, the weight, and the power is like a constant issue to have everything running. So it's all running on a single computer. So to have all the entire stack running simultaneously is just like, yes, that is a full-time job. That is several people's full-time job is trying to figure that out.
Yes, and yeah, we'll read the question before we answer. Sorry. Yes, so the question was, where's all the processing done? So everything's done on board. Okay, how different was the urban circuit environment from what you expected, and how has that informed your approach to the final?
Yeah, so in urban, it looked to us that the optimal strategy was to have a robot that could go up and down stairs. So we tried to go up and down stairs with one of our ground robots. It didn't work out so well. But the biggest thing that really informed us in urban was just how much more difficult the urban was than the tunnel circuit, just given the robots that we've had. And yeah, as we're moving towards the final competition, we're trying to take the lessons learned from both internal as well as the other teams to try to address these issues.
Yeah, and I think one other thing is that we kind of maybe overfit to some of our environments when we're testing. So try and vary the environments more to make sure that we don't overfit.
I think one of the major differences between the urban circuit and the tunnel circuit was that the urban circuit had these sort of open areas and 3D structure, whereas tunnels are tunnels. They're almost one-dimensional with some various where they fit together. Whereas the urban circuit, the environment was much more complex, and it was also very cluttered because of the way it was laid out. So there were a lot of mobility challenges that required both drones flying and also navigating stairs that weren't present in the first circuit.
And then the viewpoints, alluding to building off of what Geoff is talking about. So the reason that made it explicitly more difficult was that locating artifacts, when you're driving by them in a tunnel, doing the localization of the artifacts is actually relatively straightforward. When the artifacts can be far away and there's walls and there's three-dimensional spaces, like even locating the artifact and then localizing it within the map itself is way more difficult in urban, or was in urban.
Yep. Then the next question we got is, what is the purpose of the thermal sensors?
So the thermal, I think Shiba did a really nice job of explaining this. So the purpose of the thermal sensors is to give us redundancy in our SLAM approach. Again, Shiba did a really nice job of explaining this, of how like the thermal, the IMU, the camera, and the LiDAR all work together in sort of this like centralized, everything meets together with the IMU, and then it's this like nice story of how all the pieces fit together. So the thermal there are certain environments where thermal features are just way more apparent. We've got some initial results where we can show that in like foggy environments or things that are filled with smoke, especially where thermal typically ends up being your best sensing modality.
So I think the next two questions we can kind of combine is, so are we using a Xavier, and is the inference done on the CPU? So on the ground robots, we're using a Xavier for to detect objects. On the drones, it's actually done, so we have an Intel NUC on the drone, and the inference is done on it's called a neural compute stick from Intel for the networks. Have you tested reaction time, such as not hitting all the objects, detect and stop time? I think maybe the answer is how often are we planning, John? How often do we plan? Yes. So our reaction time is 200 milliseconds.
Yeah.
Okay. Do you train the aerial vehicle in simulation first? So how much of that knowledge is actually transferred over to the real world? So we are using simulation for development, but it's not like an AI gym where we learn some policy, right?
It's mostly for the exploration, as you might imagine, is where the simulation is most useful for us.
We are doing some research and using simulation to train for object recognition, but whether or not we use that for the final challenge sort of depends on how robust it is versus research versus systems is kind of a challenge, whether it's really ready to go on the final vehicle or not.
Yes. Are you using super odometry for the ground robots? Have you done some ground truth on accuracy location over time instead of drift at the end? So we have compared basically, survey points along in terms of drift rate. Have we done some analysis?
Yeah, we have done some analysis.
Yes, we have done analysis. So that answers the question. Okay.
Sure. How much control are you expecting to have over your system during the final, say, competition? Does having humans in the loop significantly improve performance? I'd say the opposite. From my, you can ask 10 different people and get 10 different answers, but in my understanding and what I've seen is that like having the human operator complicates things way more than you want it to. It relies on there being comms, and it relies on there being like assumptions that that'll be there, and they're not. So having the systems be as autonomous as they possibly can be, where even ground to aerial and like the team is actually working together, like that would be the best way to do this, in my personal opinion, and have like minimal operator intervention, where like maybe it might be like resolving issues amongst the different agents, but like you'd want to try to minimize, like trust the autonomy is definitely a lesson that I've learned.
Yeah, I think that was also
on urban was that if the operator has too many cameras, they could get overwhelmed very quickly. So you really need to control the amount of input that's going to the operator to make sure that they're not being overwhelmed. And DARPA has restricted this by just having the one operator that has to sit there and is only given access to, it can only do so much. So the levels of autonomy really do need to be very high to be successful.
So the next question is, are we using the same detection model on the Xavier and the drone? It's the same type of model, resolutions are a little different because of computation speeds and so on. Yeah, I mean the Xavier of course performs better in terms of GPU than the Octane compute stick, but we had to make some trade-offs. So the question is, what's the performance difference between the two? And so there's Xavier is faster than the compute stick, so there's less overhead, but you have to make certain trade-offs.
What's the prize in the challenge? I imagine a novelty check, but yeah, the prestige. I'm gonna go with Sebastian.
Yes, yeah. I mean, there's also money involved, but
hence the novelty check.
But yes, I mean, okay, thank you. Okay. How do you see your new platforms, Canary, Drone, and Spot Robot, change your strategy and performance?
Yeah.
So I think, so we have a new drone that's from Canary Aerospace that we expect to have a much longer flight time. It is a little bigger, so it can't fit through as narrow passages, but it should allow us a much wider exploration and also be hopefully a bit more stable. And the spots, and yeah, so Canary is actually is a spin out from the DARPA SubT challenge. Some of the students basically designed the drones, the initial drones, and now we have new drones that will work better, and those are upcoming. And Spot gives us a chance to work better on stills, hopefully.
Yeah, it's specialization. It's probably the short answer to that question. Right, right now, where robots are going out, and whatever. It's just an exploration strategy. Now, if you can start to have like targeted things, right? If you find a staircase, you want to use the spot, things like
that. Can your ground robot recover the drone when the battery dies?
No. So we were toying around. I'm sure everybody at some point, who's doing this type of thing is toyed around with the idea of having the drone come back and land back on the ground vehicle. But because we're going to send them off in two separate directions, and then like the exploration strategy explicitly tries to keep them apart from each other, it would probably be way too difficult.
I mean, yes. I think, based on the length of the runs for this particular challenge, there's not really a whole lot of benefit in that recovery.
That's correct.
And then, so I think your built-in, do we have built-in test? That's something that's in progress, but not right now. A lot. We have some tests. Okay, how do you see the technology being adopted in industry? So we're seeing a couple of ways that this technology is spinning out. I mean, you can see things like Canary Aerospace that makes new drones. We see some of the things where the same application is used somewhere else, but there are many similar applications as well, like inspection, tunnel mapping, for mining and so on, that are very similar. I think we are at 2 o'clock. We'll keep answering a couple more questions, but if you have to drop off, thanks a lot for tuning into our live stream experiment here. And I'll briefly show the team here that's behind the scenes. Thanks everybody for making a hard push on getting this this demo done. Thank you. And we're not done here, but that was a good first step. So we'll answer a couple more questions, and then thanks everybody. IMU-centric superdomain for the IMU-centric superdomain difficult environment. How does the system choose which sensors to listen to for correcting IMU? So that's exactly the challenge.
let's turn that question around and back on you.
Right, and so the answer might be a little too long, but basically what we're trying to find out is like how well constrained is a certain measurement. Okay. How does the robot control get affected when some sensor modalities become degraded and are dropped by the localization?
Short answer is poorly. So yeah, adding on having basically fail safes within the local planner and the low level controller is what we're working on.
Okay. Yeah, so thanks everybody for tuning in, and
yeah, thank you very much for your attention.
Hopefully it was interesting. Thank you.
Yeah.
Bye.
See you in September.